To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all electromagnetism and electromagnetic induction. This is the 13th lesson of your grade 11 science textbook. Now you are familiar with electricity. You all know how we use electricity in the household. Then you are familiar with magnets. You have learnt about magnets. I am sure you all have used magnets. But in this lesson, we are going to look at electromagnetism. How magnetism can be generated by electricity. And then electromagnetic induction. How electricity can be generated using magnetic field. So the relationship and how one another are interconnected. That is what we are going to discuss under this lesson. Electromagnetism and electromagnetic induction. So that is just the introduction to this lesson. With that, I will move on to the next slide where we look at the contents of the lesson. Electromagnetism and electromagnetic induction. It is the 13th lesson, and as you can see, it is a physics lesson. So usually electricity, magnetism, all these come under physics, a physics lesson. So under that, the first topic that we are going to discuss is magnetism. Magnetism is a property of magnets. So we will try to understand what magnetism is. You are already familiar with this concept, but we are going to discuss it in a little bit more detail. Then magnetic effect of a current. So when we supply current through a conductor, whether magnetism can be generated. That is where we discuss electromagnets. So that is what we call as magnetic effect of current. We will be discussing that. Then electromagnetic induction. So like I said, when you have a magnetic field, if there is a conductor and there is motion, there is electricity generated. So you are familiar with dynamos. Now dynamos use electromagnetic induction. Whereas electric motors, they come under magnetic effect of current. So all these are going to be discussed in this particular lesson. I am sure you can understand that. So with that introduction, students, I'll move on to the lesson. So first we have magnetism. Before I read what is given to you all, just look at this picture. This is something you all might have seen in your day-to-day life. Now this is scrap iron. Iron that has been rusted and a lot of pieces, it has been dumped in a certain area. That has to be transported to a different area. So here you can see the trucks that are ready to transport scrap iron. Now if you want to load all these iron from the ground to these transporting trucks, it needs a lot of man labor. But here you can see in this picture a large disc-like structure, a steel or iron disc-like structure that has attracted the pieces of iron. These are very large pieces of iron. How is that possible? It is possible because this particular steel structure, steel disc-like structure, is an electromagnet. Whenever needed, electricity can be supplied to this and that can become a magnet so that it will attract the iron pieces, and then when you take it to the destination, they cut off the electricity supply, so the magnetism is lost. Therefore, the scrap irons, the pieces of iron get detached from the magnet. So they get loaded to the truck. So here they are using electromagnetism, one type of magnetism. There are two types of magnets. One is the permanent magnet, the other one is the electromagnet. So what you see here is electromagnet and electromagnetism. So, if you look at the title of the diagram, use of an electromagnet to remove scrap iron and steel. So, both iron and steel get attracted to magnets, that you know. Now, if we read the introduction, figure shows the use of a large electromagnet to lift and remove scrap iron and steel. So, since iron and steel pieces are attracted towards the strong electromagnet, it is easy to move them using this method. So, that is one example where we use electromagnet. That is again an introduction to this lesson. So, with that, students, I'll move on to the next slide. So, here, like I said, there are two main types of magnets. And one is the electromagnet, the other one is the permanent magnet. Now, when we say permanent magnet, the magnetic property is always there. The bar magnets, the ring magnets, the horseshoe magnet, the U-shaped magnets, those are the magnets that we use in the laboratory for our different activities. Then there are fridge magnets, you all can remember what we stick on the fridge to hold small pieces of notes and things like that, or for decor purposes, decoration purposes, we put fridge magnets. Like that, there are magnets used in our day-to-day life which have the magnetic property always. That is, the magnetic property is there permanently. So, because of that, we call them as permanent magnets. Then, like the example we discussed before, where we use an electromagnet. That is like temporary. When electricity is being supplied, there is magnetic property, and when we stop the supply of electricity, the magnetism will not be there. So, those are coming under electromagnets. So, here you can see, in electromagnets, magnetism exists only while a current is passing through the coil of the electromagnet. So, you have to remember that. In electromagnets, magnetism exists only while the current is passing through the coil of the electromagnet. In permanent magnets, magnetism is a characteristic of the material of the magnet. Magnetism is a characteristic of the material of the magnet, and it remains in the magnet permanently. So, that is why we call it permanent magnets. So, one is the permanent magnet, the other one is the electromagnet. So, two types. You all need to know what they are. Then, you can see both types of magnets are used in many instruments for various purposes. So, if we look at the uses of some magnets, magnets are used in controlling most domestic appliances and robots. In many of the domestic appliances and robots. Now, here, if you look at this picture, you can see this is a can opener. Now, this is a can opener with a magnet there. Now, normally if you have a can made up of steel or iron, the lid is sealed to it with a, you can see the region where that will come off. When you pull it out, it comes off. You can either use a tin cutter or a magnetic tin cutter like this. You can see here when you touch it to the can. That is, the can has to be either made up of iron or steel. Then the magnet gets stuck to it attracts the lid. And when you pull it out, due to the magnetic property, the steel or the iron lid is stuck to the magnet and it comes off from the can. So, that is how we use this here. Then you are familiar with these cards, the bank cards, ATM cards, automatic teller machines. You use the cards as debit cards, credit cards. They have this part where there is magnetism. Due to magnetism, information is stored there. You all are familiar with that also, magnetic disks that store information due to their magnetic property. Then you can see this is a drill. In a drill, there is motor inside. That is why the drill is able to rotate. Like that, there are so many instruments that use electric motors. The water pumps, the fans, wherever you see this rotation or motion or movement, usually there are motors. So, there also there is magnetism used. So, these are different instances. So, here you can see different domestic appliances and robots. Robots also have magnets in them by electric motors. So, that is what I explain here. In applications involving magnetic cards, these are the magnetic cards. Then there are medical equipment such as MRI machines. Now, when we say MRI machines, it means magnetic. M stands for magnetic, R stands for resonance, and I stands for imaging. MRI means magnetic resonance imaging. So, MRI machines and in various other scientific and technological instruments. There are many other techniques. So, where we use magnetism. Is that okay, students? So, here two types of magnets, the permanent magnets and the electromagnets. They are used in various machines, devices and for various purposes. Therefore, it is useful to have a good knowledge about the behavior, operation and applications of magnets. So, because they are very useful to us in our day-to-day life as well as in many other fields. We need to know about magnetism. So, with that introduction, students, I'll move on to the next slide. Now, here you can look at this diagram. I'm sure you can understand what is shown here because you are familiar with this concept. There are objects that get attracted to the magnet. So, here you can see there are objects that are not attracted to the magnet and there are other objects that are attracted to the magnet. Now, before I discuss the slide with you all, I will go to the lab and we will look at some of these materials and try to understand whether they get attracted to the magnet or not. Okay, students. So, I am going to do this simple activity where we will be observing some objects that are attracted by magnets and some objects that are not attracted by magnets. So, I am sure you are familiar with a bar magnet. You can see here it has two colors to denote the two poles. Normally, red color indicates the north pole and the blue color indicates the south pole. It doesn't matter which end we hold, but there are some objects that get attracted to the magnet and there are other objects that do not get attracted to the magnet. So, first I have a plastic cap here. We will see whether this gets attracted to the magnet. No, it does not get attracted to the magnet. So, I will put it into this petri dish. Then I have an iron nail here. We will see whether this gets attracted. So, here of course you can see an iron nail gets attracted to magnet. So, an object that is attracted to magnet. Then a rubber, piece of rubber. So, we will see that does not get attracted to magnet. So, then I have again a button, a plastic button that also does not get attracted to magnets. Then a matchstick. Again, matchstick does not get attracted to a magnet. Then we have some pieces of paper. Pieces of paper, they also do not get attracted to magnet. Then I have some paper clips. A few paper clips, they get attracted to the magnet. So paper clips are attracted to magnet. Then rubber bands. Now rubber bands, again rubber material does not get attracted to a magnet. Then I have a safety pin. A safety pin gets attracted to magnet. Here I have some board pins. You are familiar with board pins. Now board pins also get attracted to magnet. Then I have some head pins. Now head pins, they also get attracted to magnet. The head pins get attracted to magnet. Now in this dish I have some more paper clips, safety pins and board pins, but I have already tried those out. So now I have separated out all the objects. Here you can see the objects that are not attracted to magnets. Rubber piece, rubber band, so both are made up of rubber. Then there is paper, then there is plastic, the pen cap as well as the button, they are made up of plastic. And matchstick again with wood and the part that gets undergoes combustion. So this is again a matchstick that is also made up of wood or plastic. So none of these get attracted to magnets. Normally paper, cloth, plastic, rubber, all those wood, they do not get attracted to magnets. But here in this petri dish, you can see all these materials. This is an iron nail, and you all know even safety pins, paper clips and board pins, they are all made up of either iron or steel. Depending on the quality, normally it will be either iron or steel. So materials that are made up of iron or steel, again you all know steel is an alloy of iron, so that also has iron in it. In addition to that, the metal nickel. So iron, steel, nickel. Those are the materials that get attracted to magnets. So any material that is made up of either iron, steel or nickel gets attracted to magnets. So you all have to remember that, students. Okay, students. So you were able to see I had different materials, most of them that are given in this diagram, this figure. So you were able to see the materials that get attracted to the magnet and that do not get attracted to the magnet. So if you can remember, materials like paper, wood, plastic, those do not get attracted to magnet. Even brass, copper, they are not attracted to magnets. But objects that are made up of either iron or steel, like head pins, safety pins, drawing pins, those are all attracted to the magnet. So if we look at the diagram, now here you can see when you hold a magnet, materials like these, objects like these, a plastic cap of a pen, an eraser made up of rubber, then there is rubber band, again rubber, matchstick, wood, plastic button, plastic, pieces of paper. So basically plastic, paper, rubber, wood, these are materials, even cloth, materials that are not attracted to magnets. So A is objects which are not attracted by a magnet. So here that is what you see in this first set of diagrams. On this side, B, these are materials attracted by magnets. So here you can see they get attracted to the magnets. Drawing pins. Drawing pins are usually made up of iron or steel. Normal pins, the head pins, they are again made up of iron or steel. Then paper clips, that are, although they have an insulating cover, some come with insulator covers, that is rubber or plastic cover, some do not have the cover, but still they are made up of either iron or steel. Paper clips. Then iron nails and also safety pins. All these materials are either made up of iron iron or steel. Now these materials get attracted to magnets. That is what you need to understand. All metals are not attracted to magnets. Materials like iron, steel, they get attracted to magnets. And even nickel. That is also a metal that gets attracted to magnets. So here you can see objects made of magnetic materials. That's very important. Magnetic materials such as iron, steel, nickel. So I will write that also. These are of course made up of iron and steel, but nickel also gets attracted. So objects made of magnetic materials such as iron, steel, nickel are attracted by magnets. So because these get attracted to magnets, we call them as magnetic materials. So you can use this term, magnetic materials. Materials that get attracted to magnets. So steel, iron. Now you all know iron is an element. Steel is an alloy of iron. Iron with carbon, nickel, chromium, like that, different combinations, different compositions. So steel is the alloy of iron in different compositions. So because of that, they also get attracted to magnets. Then nickel again is another metal that gets attracted to iron. So these are magnetic materials. Objects made of materials such as plastic, wood, paper and rubber are not attracted by magnets. So those are materials that are not attracted by magnets. You have to remember that. Plastic, wood, paper and rubber are not attracted by magnets. So you are familiar with these, no, students? When you all were small, maybe you would have used those pencil cases where you have the plastic pencil case with two magnets that are used to fix the lid to the pencil case. So there you would have seen, you would have even played with it. The plastic part, the rubber part, that does not get attracted to the magnet. Only the magnet and the steel part of it, they get attracted to each other. So you are familiar with this concept. With that, students, I will move on to the next slide. Now we will discuss the magnetic field. Now when we say magnetic field, now let's say if we have a magnet like that. Now here the magnetic field, now if this is a bar magnet, the effect of this magnet acts on a certain area or a region. That region is what we call as magnetic field. Normally you all know a magnet has a north and a south pole. If you take a bar magnet, there is a north pole and a south pole for that, the two poles of the magnet. And around that magnet, there is a magnetic field. I am sure you can remember that. You have learned this, discussed this in your previous grades also, in your smaller grades also. And you all know the magnetic field exists as a magnetic field lines. And there is magnetic field around it. So if you look at the magnetic field here, it is going to be something like that. And it goes from north to south like this. Those are the magnetic field lines, and it is more denser towards the two poles, the two ends, and that is how you get the magnetic field line. So to understand that, we will be doing an activity. Before that, I will go through the discussion given to you all. So here you can see magnetic field. Around any magnet, there is a region within which the magnet has an influence. So like I showed you all, within that region, within that area only, magnet has an influence. So if you have a steel object away from that magnetic field, that will not get attracted to the magnet. But once you bring it within that magnetic field, within that area only, it will get attracted. So that is where the magnet has an influence. And this region is known as the magnetic field. a magnetic field is not perceptible to the eye. Although you have the bar magnet, you can't see it with your eyes, but it is there. Therefore, we cannot see a magnetic field. However, it can influence another magnet or a moving charge. Very important. It can influence another magnet or a moving charge. It has been found that some animals, such as birds, use the Earth's magnetic field for navigation. Earth's magnetic field for navigation. Now, there are migratory birds, birds that travel across continents. These birds use the magnetic field of the Earth for their navigation purpose. You all know Earth from the North Pole to the South Pole, there is the Earth's magnetic field. So, that is there. You are familiar with that concept. So, then, one way of determining whether there is a magnetic field in a certain region is to use a compass. Now, compass is an instrument. You all have seen it. A circular display is there where you have a pointer. Normally, it is used to identify the direction. North, south, east, west, like that, to identify the direction. That is possible because there is the Earth's magnetic field and the point of the compass is also a magnet. And normally in magnets, the opposite poles attract. The North Pole attracts the South Pole and the South Pole attracts the North Pole. Based on that principle only, the indicator of the compass works. So, there we use a compass, one thing to find out the direction, in addition to that to find the magnetic field, to observe the magnetic field. So, a compass is a small lightweight magnet mounted on a pivot in such way that it could rotate freely around the pivot. That is important. So, the compass is a small lightweight magnet mounted on a pivot in such a way that it could rotate freely around the pivot. That is how you can identify the direction. In the absence of any magnetic influence other than the Earth's magnetic field, a compass aligns along the north-south direction. So, like I said, normally the indicator of the compass aligns along the north-south direction. That is how the indicator is made, the pointer is made. So, that is a compass. Compass is a small lightweight magnet, that is also a magnet. Like I said, the north of the pointer, the compass will be attracted to the South Pole. South of the compass will be attracted to the North Pole. That is how it rotates. So, you all are familiar with that. So, that is a compass is an instrument that is used to determine the magnetic field of a magnet. So, this is just a diagrammatic representation. I haven't drawn the exact correct figure, but this is how you get the magnetic field for a magnet. Towards the two poles, it's more concentrated and usually the direction is from north to south. I'm sure you all can remember that, but in the next slide, we will discuss the magnetic field and then we will observe it in the lab as well. So, that is to understand the magnetic field. So, now I am going to discuss an activity to understand the magnetic field near a magnet. So, activity: investigate the field near to a bar magnet. So, to do that, we need all these materials, the apparatus that are needed to us. The first one is a compass. I will show it in the lab also. Here, even in the diagram, you all can see, students. The directions are all marked there, and also this is the compass. So, that is the magnet that is mounted on a pivot that can rotate freely because it is light-weighted as well as it is also a magnet. So, normally this will align along the north and south because of the effect of the Earth's magnetic field. But when you bring it close to other materials, then of course the indicator, the compass, can rotate depending on the material. Sometimes it is not affected by the material if it is not a magnetic material. Otherwise, it can be affected. So that is what we are trying to understand here. So then we need all these materials for the activity. A piece of glass, then here we have iron nails, then there is a magnet, then there is a plastic cap, and then here we have brass nails. So those are the materials that we are going to use. So what we will do is we will take the compass, we will place it on a table, and if you observe, you will see that the compass, the needle, aligns along the north-south direction. That is when none of these materials are close to it. After that, what we do is we bring these materials one by one closer to the compass. And when we do that, you have to have a look at the indicator of the compass, whether it deflects or not. So this is an activity, a very simple one, which is carried out to understand the field near a bar magnet and to compare it with other materials that are given here. So I'll move on to the next slide. Here again we have the method. Place the compass on a table and observe the deflection of its indicator by bringing close to it a piece of glass, a piece of iron, a magnet, a piece of plastic and a piece of brass, one at a time. So for a piece of brass and piece of iron, we have the iron nails and the brass nails. Brass, you all know, students. What is brass? Brass is an alloy made of copper and zinc. So those are also metals. Now I told you all, students, all metals are not attracted by magnets. We saw the metals: iron, alloy of iron, steel and nickel. Those are the metals that get attracted to magnets. So that is why we call them as the magnetic materials. I'm sure you all can remember that. So this is a simple activity, students. Let's go to the lab and do the activity now. Okay, students. So now I'm going to do this activity in order to investigate the magnetic field near a bar magnet. So you're familiar with the bar magnet. You have used this before. So that is a bar magnet. And to do the activity, I have some other objects with which we will be comparing the magnetic field. So this is a piece of glass. Here I have used a glass slide, a piece of plastic, a piece of brass, a iron nail, and we have a compass here. So this is what we will be using. I will place the compass here and let the point of the compass or the compass needle to settle down, and then one by one I will hold the different objects near the compass. You will have to observe what happens to the indicator, whether it moves or not. So from that we can understand, we can investigate the magnetic field around a bar magnet. So first I will use an iron nail. If we hold the iron nail close to the compass, there is no change in the pointer. The compass remains as it is. Then I have a piece of brass. If we hold the piece of brass also around it, there is no change in the compass. Then a piece of plastic. Do you see any change? There is no change in the point of the compass. Then a piece of glass. Here you can see there's no change in the pointer. It is still in the same position. No change. Now finally, I have a piece of the bar magnet. As I bring it close itself, you can see the pointer moving. The compass changes, the pointer changes as we bring the magnet close to it. So why does this happen? Now normally the point of the compass changes due to a magnetic field. So when I bring a magnet near the compass, it rotates. That means there is a magnetic field around the bar magnet. So that is the conclusion we can get from this activity. There is a magnetic field around the bar magnet. That is why the point of the compass rotates when we bring a bar magnet close to it. Okay, students. So did you all observe the change clearly? I am sure you did. So when I brought the different materials near the compass, you saw that only when I brought the bar magnet close to it, there was deflection in the point of the compass. When I brought off the other materials, iron nails, brass nails, the plastic cap, there was no deflection at all. So from that, what can you understand? There is magnetic field around the bar magnet and the compass itself is a magnet. So when you bring a magnet towards another magnet, there is an effect. And because of that, there was a deflection in the compass. So that is how we can understand that there is a magnetic field around the bar magnet. So the observation, I have given it as a table. This is what we observe, the materials, piece of glass, piece of iron, a magnet, a piece of plastic and a piece of brass. And deflection in indicator of compass. So when there was piece of glass, no deflection. Even with piece of iron, no. With magnet, deflection. Or there was, I will write deflection observed. Here no deflection. With piece of plastic also no deflection. And with a piece of brass also there is no deflection. So only when a bar magnet was brought closer to the compass, there was deflection in the indicator of the compass. So from that, what can we conclude? There is magnetic field around the bar magnet that affects the compass. There is no magnetic field around the other materials. That is iron, brass, plastic and glass. That is why there was no deflection. So although it is the conclusion, I have included the reason as well. So these were the observations. You only saw a deflection in the compass when a magnet was brought close to it. With all the other materials, objects, there was no deflection. So from that, we are able to conclude and say there is magnetic field around the bar magnet that affects the compass. there is no magnetic field around the other materials, that is iron, brass, plastic and glass. That is why there was no deflection. I am sure you all can understand that, students. So with that, I will move on to the next slide. So this is for your extra knowledge. Naturally occurring magnets have been known to man as far back as thousands of years. The compass was invented by Chinese in the 11th century AD, Anno Domini, that is after the birth of the Christ. So Chinese in the 11th century AD. Now we are in the 21st century. So this was actually 10 centuries ago. In the 11th century itself, the compass was invented. The compass was invented by the Chinese in the 11th century AD. So that means man has known about the magnets for a very, very long time. So this is just for your extra knowledge. So you all know, students, even from the ancient times, there were explorers and travelers who travel from one continent to the other. And they were able to do that by sea because they had the compass. Using the compass only, they were able to identify the directions. Otherwise, when you are in the middle of the ocean, you all don't know which direction you are traveling in. So to find that, they had these compasses that helped them a lot. And as you can see, the compass was invented a very, very long time ago, 10 centuries before now. So that is how long ago the man knew about magnetic field. So that is something that you need to know as extra knowledge. So with that, students, I will move on to the next slide. So here, we again explore the magnetic field. When a compass is placed at a point in a region where a magnetic field exists, the direction of the compass needle shows the direction of the magnetic field at that point. So that is something you need to know. The direction of the compass needle shows the direction of the magnetic field at that point. So this is how we use the compass to identify the magnetic field of different magnets. This direction can vary from point to point. In addition, the strength of the magnetic field can also vary from point to point. So something you need to remember. The direction can vary from point to point, and the strength of the magnetic field can also vary from point to point. Therefore, a magnetic field is a physical quantity with magnitude and direction. It has both magnitude and direction. How is that possible? Now here you can see the bar magnet. Earlier also I showed you all this in a diagram. We will be doing an activity related to this. Here you can see there are arrowheads. These arrowheads point to the direction of the magnetic field. And also, like I told you all, near the two poles, the north and the south poles, the magnetic field has more strength. As you go away from the magnet, the strength of the magnetic field decreases. So when we say strength, there is a magnitude to the magnetic field. So it is a physical quantity with a magnitude and a direction. Is that clear, students? So that is how the magnetic field is for different magnets. Now in this diagram, you can see finding the direction of a magnetic field using a compass. So this is a bar magnet. This is what we are going to do. We will place a white sheet of paper on the table, and on that we will place a bar magnet, and then we will hold the compass starting from one end. Starting from the North Pole, we will move the compass towards the South Pole, and while moving it, you observe the direction of the needle of the compass and you draw them, mark those directions. Like that, we do it at different points, and thereafter, when you connect those points, you will get these magnetic field lines. Then you can observe that there is magnitude and direction. This is for a bar magnet. Now here you can see this is a U magnet. Now when we have a U magnet, one end is the north pole, the other end is the south pole. Normally it is the convention, students. We use red color or maroon color to denote the north pole of the magnet, and blue color, they are also blue color, to denote the south pole of the magnet. So we will be doing for both these magnets, for the bar magnet and for the U magnet. So that is to identify the magnetic field and to understand that magnetic field is a physical quantity that has a magnitude and a direction. So let's go to the lab and do the activity now. Okay, students. So now I am going to do this activity in order to observe the magnetic field of two different types of magnets. So I will be using a bar magnet, a U magnet, and also a compass to observe the magnetic field. And what we will be doing is, I will first place the bar magnet on this white paper. Then using the compass, we will observe the direction of the pointer that directs to the magnetic field, and then we will draw the magnetic field line. So here I have placed the magnet. Just an outline of the magnet. And that's the north, that's the south. So then if we hold the magnetic, now compass, you can see when I move it above the magnet, you can see the pointer deflecting. So first what I will do is, I will place it here. So here if you see, we will have to let the pointer to settle down. Can you see there? Now this is south, north, and the pointer, the red color, points to the north. So there you can see the direction of the magnetic field is in this direction. So if I move it here, if I mark it with an arrow, it is going to be in this direction. Let's say now if I move it somewhere here. Now observe what happens. Now can you see what happens to the magnetic field? It has turned at an angle. So here it is going to be in this direction. When I move it somewhere to this point, here you can see the magnetic field turning like that. So if we bring it to this point, so here we had the first line, then here we had the second arrow. So until this settles down. Now in this you can see the pointer moves in this direction. It points to this direction. The red color arrow, it's towards this direction. Then when I bring it somewhere here. Now can you see the pointer? It is pointing towards this direction. If I bring it to this point along with the pointer, now again you can see north is pointed towards the south pole of the magnet. So it's towards this direction. So this is in one side how the magnetic field is. The same way we can have the compass here. If I let it to settle down, here you can see it is going to be in this direction. You can see the pointer. Then if I move it to somewhere here, so at this point, it will be towards this direction. And then if I bring it to this point. Now here you can see again the arrow points towards this direction. So now if we connect all these lines, here you can see it goes this way. So here if we connect the lines, they get connected in this manner. So at the two ends, if we have the magnets, the two ends, the magnetic field is more concentrated, and from north you can see the field line pointing outwards, and from north to south you can see on either side the field line moving from north to south. This side also from north to south, and here again there are magnetic field lines facing towards the south. That is how it happens. Now just to confirm our observation, if we look at the field, now here you can see. Now the indicator, we will wait till it settles down. It points towards the north. When we bring it to this point, now here you can see it going this way. And when we bring it to this point somewhere here, it is pointing to this direction. Then if I bring it to this point, now here you can see the pointer pointing towards this direction. And here again, it points towards the south pole of the magnet. The same way on this side, we need to wait until it settles down. So here you can see the pointer points in this direction. Then if we bring it here, you can see the pointer pointing towards this direction. So again if we bring it, now here you can see it points towards the south. So that is how the magnetic field of a bar magnet is. Now after this we will observe the magnetic field of a U magnet. So here I have the U magnet there. Again I'll draw the outline of a U magnet. So here we have the north and the south. Those are the main things that we need. So then if we are to observe the field here. So here if I bring it closer, you can see the pointer deflecting. So that means there is a magnetic field. So now if I hold the magnet here. Now for this of course, because it is a U magnet, we will have to hold it over the magnet. Now I need to let it to settle down. The pointer has to settle down. Here you can see it comes from south to north. Now here you know this is the north end of the magnet. Here it is the south that settles down there. And this side north. So from north to south, the magnetic field. Even if I bring it here, but when we bring it near the U part, then of course it changes. But towards the arms, you can see it settles down this way. So from this, you can understand the field lines going like that. The field lines are going this way. So that is the north and south, the field lines are going that way. That is how the magnetic field is for a U magnet. Now we will compare both the magnetic fields. So here you can see, students, this is for the U magnet. You have the north to south. The field lines are in this direction, north to south. Now here also you can see the north of the magnet, south of the magnet, like this. From here the field lines come out from the north pole. So and they go towards the south pole of the magnet. So here also you can see they move towards the south pole of magnet. So both magnets have the magnetic field lines. So it is a quantity that has a magnitude as well as a direction. You can see the direction of the magnetic field. So I am sure you all can understand that concept with this particular activity. Okay, students. So in the lab you were able to observe the magnetic field of the magnets. So the different magnets, one is the bar magnet and the U magnet. So when I did the activity, when you have a piece of white paper, on that you place the magnet and then you use the compass to identify the direction. So you were able to look closely how the needle of the compass changes direction. It always points towards the north. Then you know how the magnetic field lines are. They start from the north, go towards the south. And there is magnetic field on either side of the magnet. This is how you get the magnetic field for the bar magnet. And the same way, here you have the magnetic field of the U magnet. So that is how the magnetic field of a magnet exists. A physical quantity with a magnitude and a direction. So with that introduction, students, now the magnets that we have understood here are the permanent magnets. We started off the lesson by discussing the two types, the permanent magnet and the electromagnet. I did not go into detail about the electromagnet. We were discussing the magnetic field, how different materials get attracted to magnets, and then the magnetic field of permanent magnets. So with that, students, I am going to end this chapter, and in the next chapter we will try to understand the magnetic effect of current.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.